Hey guys, last time I promised to tell you a little bit about what is it that I'm doing as a computational physics PhD student and what is my research all about and what it is that I will be working on for the foreseeable future, maybe even for the rest of this year, because as a physics PhD student, at least in my area of research, you are required to complete 2 large projects throughout your PhD and at least have started a third one. Now the 4 keywords for today's discussion are nanoparticles, code, GPU acceleration, and Monte Carlo. But don't worry, I'm not going to bog you down with too many technical details. I'm just going to provide you enough context for you to be able to understand the exact nature of my research. Let's start with the basics. There are many types of nanoparticles, classified by the material they are made from. And the choice of that material greatly depends on the intended application. For example, nanoparticles can be made from pure metals like gold, copper, iron, and a few others. And another example is metal oxides, where in addition to the metal there is added oxygen, and the addition of the oxygen greatly changes the properties of the nanoparticles. So all these different types of nanoparticles have many applications, starting from medicine to environmental science, or even simple everyday products like your sunscreen. My research focuses specifically on magnetic nanoparticles, which have their own unique set of fascinating properties and uses. But here is the catch. Understanding their properties is like poking a black box. You never know what comes out of it. So you first make your nanoparticles and then you characterize them using various characterization techniques. And then you try to understand those properties and what they can be good for. So making nanoparticles is not difficult in principle. But as many things in the lab, it costs time and money. And this approach does not always give you something exciting. But what if we could flip that process around? First, characterize them, assess their properties, and then proceed to making them. So the only way to do it this way is to use code and laws of physics, like specifically the laws of magnetism at the nanoscale. So any models used for writing any sort of code are very simplified models. But they still should capture the essential features and hopefully provide us with enough information to give us a blueprint for making real physical nanoparticles with the desired property in mind. And another usefulness of the computational modeling approach first is the hope to be able to understand better some of the experimental results that have already been collected. It is always easier to change some of the parameters on the computer than in the lab, especially once you make the sample. There are some cases where we know what the results are, but sometimes we're not so sure why a certain thing is happening. So playing around with some parameters in the program, if you have one, might really save you a lot of time and trouble, and hopefully give you some clues to where to go next. Now my task is to find a good enough simplified model, at least for one kind of nanoparticles, because as I said, there are many, not to mention the material, but also different shapes. And that would mimic a real nanoparticle behavior, close enough at least. And not only a single one, but the more interesting case would be the interaction of many such particles, because any sort of material is made up of more than one. Then once we come up with a good, simplest possible model, first step is then usually to test it. And once the particle is behaving as expected, then we can scale up the simulation to simulate groups of such particles. This is actually a standard approach in physics simulation development. So there's nothing new here in itself. For example, the Ising model is a classical example in physics where we use such simplified model to represent complex physical phenomena and complex magnetic phenomena in magnetic systems. A single Ising spin models a single magnetic dipole, and then the array of those Ising spins will represent the collective behavior of those Ising-like magnetic particles, and with that we could deduce some of the properties of the material. But there are some caveats, or whatever the right word is, or showstoppers to this approach. It's not always possible to use it, and we will come back to this in a moment. Things are not so simple with nanoparticles. We cannot simply just apply Ising approximation to every nanoparticle. Now, also one of the things to consider when developing a physics simulation is the computational complexity, because computation is not free. Not only costs you time to write the code, test it, debug it, and so on, but it also costs quite a bit of energy to run those simulations a lot of times. Some of my simulations back in my early master's degree days took actually weeks to run. That's an example where the code was not parallelized enough or not optimized enough as well. So there's a lot of things to consider when developing simulations that require a lot of interactions to be calculated, because trying to calculate all possible interactions between pairs of particles and unique pairs of particles computationally is quite heavy on the resources, because there's a lot of such interactions to compute. And then from those interactions we can deduce quantities like energy, magnetization, susceptibility, and so on. And on top of that, if we run a Monte Carlo simulation, then these calculations have to be repeated over and over and over again with each Monte Carlo step. So in simple terms, when we design a simulation, there is always, or at least in my research area, I can't talk for everything else, but if we talk about Monte Carlo specifically, there is always a part that runs sequentially. So for example, Monte Carlo steps, and there's also a part to it that will be able to run in parallel as long as you set it up correct. For example, calculations inside each Monte Carlo step can often be parallelized, and quite a bit. And this parallel part is exactly where I am hoping to implement GPU acceleration to the max possible ability of me being able to write that code, and also maximize the compute capacity of like modern GPU cards. And again, technically there is nothing new to simulating large assemblies of nanoparticles. The idea of using simulations for nanoparticle research and development has been around for quite a while. Many researchers use these techniques to do their calculations and predict something that they want to predict. And there's also no single universal Monte Carlo program or algorithm that will give you the best possible runtime or results. It's very specific to the problem you're doing, it's specific to how you set it up as well. And as with everything, there's always room for improvement, even for existing well-established methods, especially with the rapid rise of modern large memory GPUs and machine learning techniques that find its way more and more into physics research. So in some of my previous videos, I believe I mentioned how I studied artificial spin-ice systems during my master's program. And in essence, those artificial spin-ice elements, like the building blocks of the ASI systems, are nothing else than nanoparticles, because they also have the same nanoscale dimensions just as nanoparticles. The ASI elements are typically arranged on some sort of geometrical lattice, they have elongated shape, and their orientation is typically also fixed inside the material. So the only thing that can change in that type of systems is the magnetization direction of each element. It can switch either in one or the other direction, that's it. And so this is the sort of thing I was studying throughout my master's. So studying those interactions and tweaking them and looking at the results. So if you are interested in the outcome of this type of work, you can look it up on my webpage under publications, where I have put a link to my master's thesis where this work is described with some nice pretty figures. So now, what's the difference between ASI elements and nanoparticles? So one of the main differences is, of course, the shape. So now the shape of the nanoparticles can greatly vary. They can be spheres, cubes, rods. You can really get creative here. So because of the shape, now the magnetization of each element can have many different possible directions in space, not just two, as in ASI elements. They're also not typically arranged on a lattice. So they are sort of randomly arranged in a plane or throughout the material, and the relative orientation of each particle is random, as well as the spacing is not very fixed. It can be controlled a little bit, but it's typically not super strict as in artificial spin-ice systems. And so this randomness and various sizes and shapes introduce a layer of complexity, so we no longer can model them as simple Ising spins. This difference as compared to simple ASI elements makes computational modeling quite challenging. I'm ready to tackle it. I hope this was more or less clear introduction to what I will be doing for my PhD, or at least for part of it. And if you have any questions, leave them in the comments. I will try to answer them to the best of my ability. The only thing that can possibly interfere is, of course, giving away too much detail, because there is, academic copyright involved, and so you can't really overshare. You can't share the exact details of what you're doing, but still, I think I gave you enough of an idea of my work. So I hope this was interesting. Let me know, and I'll talk to you next time. Bye, guys.